Now we will begin our explanation related to Thermistor Workshop Basics, Part 3, Design Support in SimSurfing. As we described in Part 1, NTC Thermistors and Temperature Sensor Circuits, and Part 2, Temperature Sensor Circuit Creation and Use Examples, we can obtain information related to the temperature and voltage relational expression, temperature sensor circuit or R1 selection, and temperature accuracy calculation, which we will need in order to create a temperature sensor using a thermistor from the SimSurfing NTC Thermistor Operation Simulator on the Murata manufacturing website. To open the SimSurfing NTC Thermistor Operation Simulator, visit the Murata manufacturing website and perform the following steps. The circuit constants and temperature and voltage relational expression used when creating the circuit as described in Part 2, Temperature Sensor Circuit Creation and Use Examples can all be derived by using SimSurfing. The specific conditions are as follows. The temperature range used for this simulation is -20 degrees Celsius to 85 degrees Celsius. We will now derive the expression that shows the relationship between temperature and voltage through the following process, which consists of 10 steps. 1. From the two available tags, NTC Thermistors for consumer application and NTC Thermistors for automotive high reliability application, select NTC Thermistors for automotive high reliability application. 2. In the part number search field, enter NSU15XH103 as the thermistor part number and select NSU15XH103F6RC. 3. Among the circuits shown, select the one with the thermistor on the ground side and resistor R1 on the power supply side. 4. Click the Simulation button. 5. Next, specify the applied voltage. We will use the default value of 3V, but this can also be changed to another value such as 3.3V or 5V. 6. Click the Tool button to open the setting table. 7. We want to use a temperature range of -20 degrees Celsius to 85 degrees Celsius, so enter -20 in the temp_L field and 85 in the temp_H field. 8. Check the box next to temperature approximation and select 5-4 degree. To obtain a balance between the accuracy of the relational expression and the processing load on the microcontroller, we will select a quintic degree 5 expression. Using a primary degree 1 expression will reduce the processing load on the microcontroller, but the temperature accuracy will be poor. Using an octic degree 8 expression will improve the temperature accuracy, but the processing load on the microcontroller will be high. After entering the above, click the OK button. The recommended value for resistor R1 to match the conditions specified is displayed here. Next, we will now explain how the recommended R1 value is calculated. The recommended value is the resistance value at which the voltage change is greatest at the center value of the temperature range. As this graph shows, the slope of the graph showing the relationship between temperature and voltage changes according to the resistance value of resistor R1. The greater the change in voltage per unit of temperature, the higher the temperature sensing accuracy. This means that we can increase the temperature sensing accuracy by optimizing the resistance values of voltage divider resistor R1 and the thermistor to match the temperature range to be measured. The temperature sensing accuracy is better near 60 degrees Celsius for a resistance value of 2.2 kΩ, indicated in red, near 40 degrees Celsius for a resistance value of 6.2 kΩ, indicated in green, and near 0 degrees Celsius for a resistance value of 22 kΩ, indicated in blue. In addition, SimSurfing can output 4 simulation results to match the conditions we enter. The first is a graph showing the relationship between temperature and voltage. The quintic degree 5 expression is also shown in the lower section. Once this relational expression has been input to the microcontroller can output the thermistor's temperature. The second is a graph showing the relationship between temperature error and temperature. It shows the temperature accuracy taking into account tolerance in thermistors, resistors, and power supply voltage. The third is a graph showing the relationship between resistance value and temperature. This also shows the effects of tolerance of resistance and the B constant due to the temperature of the thermistor. The fourth is a graph showing the relationship between voltage error and temperature. It shows unevenness in the voltage output to Vout due to tolerance in thermistors, resistors, and power supply voltage. In Thermistor Workshop Basics, Part 3, Design Support in SimSurfing, we explained how to derive the information you will need to design a temperature sensor circuit with a thermistor. As you observed, this information can be obtained by following a simple procedure. Thank you for your attention.